Hello and welcome to this presentation related to trigonometric proofs. Here we're going to use basic trigonometry and Pythagoras' theorem to derive the proof for various formulae stated within the respective problems. This is an unusual approach for us as technician engineers, as generally speaking most of our solutions are related to solving practical problems numerically, but this time we're going to solve them algebraically. So for the sketch shown here, in previous calculations, we've determined the value of height h numerically, given various parameters such as the angles and lengths. But here we're going to derive a formula for height h as an algebraic expression, shown here. Presentation overview. We'll commence with a very brief recap of Pythagoras' theorem, basic trigonometry, some terminology related to angles of elevation and depression, and a formula we'll use for calculating areas. The presentation commences with example 1a, which uses basic trig to solve a very simple problem, and example 2a, which again uses basic trig, but this time we have to generate two equations, so we solve these equations simultaneously to find the solution. The examples are worked through in detail on the slides. And then we have questions 1a through to 6a for you to attempt at your own pace, although the full worked solutions are shown. And finally, questions 7a to 10a are left for you to attempt at your own pace and to develop your own solutions. And here are the approximate start times related to the various sections contained within the presentation, but please note that these times are rounded to the nearest minute. And here for your further information are the first 6 questions contained within the presentation that include full worked solutions. So if you want to skip to question 1a and question 2a, here are the approximate start times for these questions. Question 3a, question 4a, approximate start times. And question 5a, question 6a, start times. Hopefully this may aid your ease of access through the presentation, but as mentioned previously, these start times are rounded to the nearest minute. So trigonometric proofs solved using basic trigonometry. So the following questions we're going to consider will state formulae that are to be proved making use of basic trigonometry, that's the sine, cosine and tangent functions, Pythagoras' theorem, transposing or rearranging equations, and often requiring us to generate simultaneous equations. Here's a few slides recapping our previous presentations. Here are the trigonometric ratios. Always remember that they only apply to right-angled triangles. In our previous presentation, we considered the mnemonic SOHCAHTOA, a way of defining the various trig ratios. For sine of the angle theta is the opposite side divided by the hypotenuse side of a triangle, labelled here. The cosine of angle theta is the adjacent side divided by the hypotenuse, shown here. And the tan of angle theta is the opposite side divided by the adjacent side of a right-angled triangle, shown here. The sine, cos and tan functions are usually pre-programmed into our scientific calculators. Trigonometric ratios continued. Also be aware that the tan function, so tan theta, can be defined as the sine theta function divided by the cos theta function. And also from previous presentations, we know that cosec is the reciprocal of the sine function, secant or sec is the reciprocal of the cos function, and cotangent or cot theta is the reciprocal of the tan function. These functions are not usually built into your calculator. Here's Pythagoras' theorem, again only applies to right-angled triangles. For the nomenclature shown in the sketch, Pythagoras' theorem states that the square of the hypotenuse labelled as C in this case, is the sum of the squares of the other two sides. So in this case that's a squared added to b squared. And various rearrangements are shown here for reference. Some terminology here. Angle of elevation. So angle theta is measured between the horizontal and the line of sight when looking up at an object. So angle theta shown here is the angle of elevation. Angle of depression. Angle theta measured between the horizontal and the line of sight when looking down on an object. So angle theta here is the angle of depression. And finally, formulae for area of a triangle. Area of the triangle shown in the sketch can be calculated from a half base multiplied by height, or from the formula a half side length b multiplied by c multiplied by the sine of angle A. Let's consider example 1a, a fairly straightforward exercise, but hopefully it illustrates what we mean by showing or proving the formulae given. The angle of depression, labelled A, of a boat viewed at a particular instant from the top of the lighthouse of height h is shown in the sketch below. Here's the angle of depression A. Assuming that the lighthouse is located at sea level, we've got to show that the distance x of the boat from the base of the lighthouse is given by x is equal to h divided by tan of angle A. Here's x on a diagram. So noting this right angle triangle here, then the opposite side of the triangle is height h, and the adjacent side of the triangle is length x. So from the basic trig relationship, tan of A is equal to the opposite side divided by the adjacent side. We can rearrange the formula for distance x, and that's simply h divided by tan of angle A. Hence we prove the expression given in the example. And that's the essence of what we're going to try and do with all problems. We're going to show how to derive the formula as stated in the problem. Let's consider example 2a. An isosceles triangle shown in the sketch here. Don't forget, an isosceles triangle has two sides of the same length and two angles the same. Has a length or height of L shown here. We're asked to show that the area of this isosceles triangle is equal to L squared multiplied by the tan of angle x, where angle x is half of angle alpha is shown here. So to solve this problem, we're going to generate two equations, one generated from the formula for area of the triangle and one generated from our basic trig tangent ratio. So first of all, the area is calculated from the formula b multiplied by L divided by 2. First dimension b of our triangle, we've called this equation 1. And then from basic trigonometry, we know tangent of alpha divided by 2, half of angle alpha shown here, is equal to b upon 2 divided by L. Here's angle alpha divided by 2. What I've done on the next line is simplify the expression, because b divided by 2 divided by L can be written as b divided by 2L. And then I've rearranged the equation for b, multiplying both sides by 2L. That's equation 2. What we do now is substitute equation 2 into equation 1. So we have area is equal to 2L tan alpha divided by 2. That's multiplied by L upon 2. So simplifying, we can write that as A is equal to L squared multiplied by tan of x, where angle x is actually alpha divided by 2. L squared occurs because of the L multiplied by L here, produces L squared, and the alpha upon 2 becomes the x. So those two examples try to illustrate the type of problems we're going to solve by essentially proving the formula stated in the question. I'm now going to outline an array of questions, which I would encourage you to stop the presentation and to attempt, but I will very briefly overview the full work solutions. Within each of the questions, I would strongly encourage you to try and sketch a diagram of the particular problem being outlined, as that helps with understanding of the question and also helps with developing the solution to the problem. So question 1a. The altitude of the Sun was known to be at an angle theta to the horizontal. The length of the horizontal shadow cast by a chimney was dimension L. We've got to show that height h of the chimney is given by h is equal to L multiplied by tan of angle theta. I would encourage you to stop the presentation, attempt question 1a, but the full solution is shown on the following slides. So question 1a, here's the solution. The first thing to do is to sketch a diagram of the chimney. Height h, shadow cast is length L. And from basic trig, we can clearly see that tan of angle theta is equal to the opposite side labelled as h, divided by the adjacent side labelled as L. So simply rearranging, height h is equal to L multiplied by tan of theta. And that proves the formula stated in the question. Question 2a. Given the geometry in the sketch on the right hand side, we've got to prove the following for length BD. So BD is equal to the square root of, in brackets, AB squared minus AD squared plus CD squared minus CD. As a hint, we need to consider the two triangles shown, generate two simultaneous equations from Pythagoras theorem, and then solve to find length BD. BD shown here. I'd encourage you to stop the presentation and attempt question 2a. But the full work solution is shown on the following slides. So question 2a, here's the beginning of the solution. So we're going to use Pythagoras theorem here. Step 1, I've considered triangle ACD, this triangle here. I'm going to find length y of this triangle shown here. And of course dimension y is actually AC, labelled on the diagram here. Length AD squared is equal to length CD squared added to length AC squared. And I'll essentially rearrange the equation first of all for AC squared and then for AC by square rooting both sides of the equation. So I have equation 1 formed here. Question 2a, solution continued. Just repeated equation 1 from the previous slide for convenience. So step 2 shown here, I'm going to consider triangle ABC. ABC. This time I'm going to find length Z of this triangle. Notice length Z shown here on our sketch. And of course length Z is labelled BC on our triangle here. So length AB squared, so hypotenuse shown here, is equal to length BC squared. That's actually dimension Z, added to length AC squared, shown here. I've called that equation 2. So now I've got two equations. I'm going to use the substitution method here, and I'll substitute equation 1 into equation 2. So here's equation 1 inserted to equation 2. And notice here that the square root and the squared operation cancels. Now I rearrange the equation to make BC the subject. So initially I subtract this bracket from both sides of the equation. I then square root both sides of the equation to leave BC as the subject of the equation. Now the question wants us to determine length BD. So length BD is simply length BC, this length across here, minus length CD, this length across here. So BD is equal to BC, determined above, minus CD. So now we prove the formula given in the question. Here's question 3a. The isosceles triangle shown in the sketch on the right here has an altitude labelled h shown here and an area, symbol A. We've got to show that angle x, shown here, is equal to 2 multiplied by the inverse tan of A multiplied by h to the negative 2. So as a hint in this question, we're going to need to generate two equations, one using the formula for area of a triangle and one related to the use of basic trig. From the equations, we'll be able to solve for angle x. I'd encourage you to stop the presentation and attempt question 3a, but the full work solution is shown on the following slide. So question 3a, here's the solution. Initially, let's consider the formula for area of a triangle. That's the base b, labelled here on my diagram, multiplied by the altitude or the height of the triangle h divided by 2. Call that equation 1. And from basic trig, tan of angle x divided by 2, so half of this angle, is equal to the base divided by 2 divided by height h. Here's a more detailed diagram to illustrate the right-angled triangle we're considering here, in yellow. So here's angle x divided by 2. Here's the opposite side, b divided by 2. And here's the adjacent side, the height h. Our next line, we've got tan of x divided by 2 is equal to b, this time divided by twice the h. Note from the line above, that's b divided by 2, and then divided by h, so that's the same as b divided by 2h. And then rearranging for b, we simply multiply both sides by 2h, so we have 2h multiplied by the tan of x divided by 2. Call that equation 2 for reference. So now we have two equations generated, we'll solve them simultaneously. So we're going to substitute equation 2 into equation 1. So here's equation 2 substituted for symbol b in equation 1. On the next line, we simply multiply the two h terms together. H here multiplied by this h here produces h squared. And the 2 in the numerator cancels with the 2 in the denominator shown here. So we're left with the formula A is equal to h squared multiplied by the tan of x divided by 2. Rearranging for tan of x divided by 2, we simply divide both sides by h squared. Then taking the inverse tans or arctans of both sides of the equation is equal to tan to the negative 1 of the area divided by the h squared. Finally multiplying by 2. So x is equal to 2 multiplied by the tan to the negative 1 of a divided by h squared, and of course the h squared could be written as h to the negative 2. So again, we've solved the problem given to us in the question. Question 4a, for the trapezium, illustrated in the sketch on the right hand side here, we've got to show that the area is calculated from the formula as stated here. The overall approach to the solution for question 4a is very similar to that for question 3a. We have to use the formula for the area of a trapezium, shown here for reference, to generate one equation, and then generate a second equation using basic trigonometry, considering the geometry of the section. Just note for reference, in the formula we're trying to prove, there is no height h stated. So I'd encourage you to stop the presentation and attempt question 4a, but the full work solution is shown on the following slide. Here's question 4a, the solution. So initially we generate an equation based on the formula for the area of a trapezium, shown here as equation 1. Next we use basic trig, the tan function here, tan of angle theta, to generate a second equation. Here's the right angled triangle we're considering, where the opposite side of the triangle is the capital B minus lowercase b dimension, and the adjacent side, of course, is height h. We've rearranged the equation in terms of height h because in the formula we're trying to prove there is no height h, so we're going to eliminate height h from the equation with our simultaneous equation solution process. So this is equation 2. We now substitute equation 2 into equation 1. So here's equation 2 placed into equation 1 for height h. And if you expand this binomial bracket with this binomial bracket, that will simplify to the capital B squared minus lowercase b squared. And notice we're dividing this numerator here by tan theta and then by 2. So that's the same as dividing the numerator by 2 multiplied by tan theta. All that's happened on the last line, instead of dividing by 2, I'm going to multiply by 1/2. And again, we've solved the problem stated in the question. Here's question 5a. Problem very similar to that of question 4a. Again, we have a trapezium shown in the sketch. We've got to prove the following formula, noting that A is again the area of the trapezium. So we'll need to make use of this equation again. And here's the formula we have to prove for angle theta. I'd encourage you to start the presentation, attempt question 5a, very similar approach to that of question 4a. Full work solution shown on the following slide. So question 5a, here's the solution. I'll let you review this at your own pace. As I said, it's very similar to that of question 4a. Here's our first equation for area. Here's our second equation in terms of height h. And again, solving simultaneously, we'll substitute equation 2 into equation 1. You can see that our final solution here is the same as that we're asked to prove in the question. Question 6a. A person cycles S1 kilometers due south and then E1 kilometers due east. Another person, starting from the same point as the first person, cycles E2 kilometers due east and S2 kilometers due south. Note that distance E2 is longer than distance E1 and distance S1 is longer than distance S2. If Z is the final distance between the two people, we've got to show that Z is equal to the square root of, in brackets, E2 minus E1 all squared, added to, in brackets, S1 minus S2 all squared. Hint in the question is to sketch proportionally the diagram of the two journeys, commencing from the same starting point in the directions as stated above. You should ultimately form a right-angled triangle from which you can use Pythagoras' theorem to determine the distance between the people, labelled as Z. I would encourage you to start the presentation and attempt question 6a, but the full work solution is shown on the following slide. Question 6a, here's the full work solution. Here's a sketch of the diagram related to the information given. First person cycles S1 kilometers due south, drawn here. E1 kilometers due east, here. The second person travels E2 kilometers due east and then S2 kilometers due south, here. Z shown here is the distance between the two endpoints of the people's journeys. So next we'll calculate dimension x, and x is equal to E2 minus E1, and we'll calculate dimension y, and y is S1 minus S2. So essentially we're forming this right-angled triangle shown here. So applying Pythagoras' theorem, square of the hypotenuse, that's z squared, is equal to x squared plus y squared. And simply square rooting both sides, we find the solution to the problem. The formula we were given to prove, we now have. Question 7a. A cylindrical fuel tank on a lorry has a diameter d and length L. D and L shown here in the sketch. Considering the mass density, symbol ρ, gravitational acceleration, symbol g, and the volume of the cylinder, v, calculated from the formula quarter multiplied by pi multiplied by d squared multiplied by L, we're asked to show that the diameter of the tank can be expressed by the equation shown here. Note that W relates to the weight of the cylinder, and that's calculated from the formula W is equal to rho g v. I'd encourage you to stop the presentation and attempt question 7a and try to develop your own solution to derive this equation. Question 8a. A rectangular watertight box that floats on water has dimensions of length L, width B, and overall depth capital D. If the box has a weight W, we're asked to show that the depth to which the box is submerged in the water, lowercase d, is given by the formula shown. Note symbol ρ is mass density, g is gravitational acceleration. There's a hint here that this problem makes use of Archimedes' principle, which we reviewed in a previous presentation. In other words, the upthrust on the body, labelled WU, equals the weight W of the water displaced. And upthrust WU is equal to the volume of the water displaced multiplied by ρ multiplied by g. Again, I would encourage you to start the presentation and attempt question 8a and develop your own solution, and so determine the relationship for submerged depth of the box. I'll let you review question 9a at your own pace, generate appropriate equations and solve. We're trying to find the relationship between height h of the elevation of the wall. And finally question 10a. Again, I'll let you review this at your own pace. In part 1, we have to show the relationship for y, just to mention y here, and the answer for part 2, shown here, part 3, shown here. Again, I'd encourage you to stop the presentation and attempt question 10a, developing your own solution to the problem. I hope this presentation has been of interest to you, and as always, thank you for viewing.